Hello everyone, welcome to this session of the course on deep generative models. In this session, we will be looking at a class of generative models based on a principle called variational divergence minimization. The famous generative adversarial networks or GANs are also a member of this family of generative models. Now, before we go into the details of variational divergence minimization, I would quickly recap the concepts that we saw in the previous session so that there is continuity. Now, in the previous session, we looked at a formal definition of what generative modeling is. Recall, what we are given is a data set, which is a set of n samples drawn IID, independently identically distributed, from an underlying unknown distribution, which we denote by script px. Now, given this, the goal is to estimate the underlying distribution px and learn to sample from it. So, as I said in the previous session, estimating px may be implicit or explicit depending upon what model are we looking at. But one of the primary requirements of a generative model is to learn to sample from the unknown underlying distribution, in this case px. Now, we also looked at what is a general principle of learning generative models. I told you that it involves three broad steps as a recipe. The first thing is to assume a parametric family on px denoted by p theta. So, typically in modern day generative models, this p theta is represented using deep neural networks, and this is what is referred to as a model. Okay. Then once you represent the underlying distribution using some parametric model p theta, now one has to define and estimate a divergence metric between the true distribution px and the model distribution p theta. The next step is to solve an optimization problem over the parameters of p theta, the model distribution, with a goal of minimizing the aforementioned divergence metric that would capture the distance between p theta and px. Now, the idea is to set the parameters of this parametric distribution p theta in such a way that it approaches px as closely as possible. We also looked at an example of a class of methods that are called push forward methods, where the idea is to start with an arbitrary random variable from which we know how to sample from. So, typical choice would be a normal distribution with zero mean and unit variance, and then represent your p theta as the distribution obtained from the output of a deterministic function g theta that would map the samples from the space of z, from which the random variable is sampled, to the space of data denoted by script x. Now, what happens is that by the elementary probability theory, we know that a random variable, when pushed forward, pushed through a deterministic function, will lead to another random variable denoted by x cap in this case, and will have a different distribution as compared to the distribution of the initial random variable that was used as an input. Now, the probability distribution of the output random variable determines on what sort of function is d theta. Okay. So, the idea in these classes of generative models which uses a push forward mechanism is to represent the function d theta as a deep neural network. Okay. And the distribution that this particular neural network is imposing is denoted by p theta. Okay. Then the idea is to start from an arbitrary distribution, which often happens to be a normal distribution, pass it through a deterministic neural network, and obtain the samples from some distribution denoted by p theta. Please note that the output of this neural network is only giving us samples from p theta, but not the distribution p theta itself. Okay. Then as we saw, the objective is set as a minimization, an optimization problem over the parameter space of this particular function, in this case a neural network, such that a distributional divergence metric between the true distribution and the distribution that is imposed by the model is minimized. Now the hope is that if the distributional divergence metric is well defined and the optimization problem is solved appropriately, then when the optimization is solved and you reach the optimal set of parameters theta star, the distribution that is imposed by this neural network p theta would have gone close to the true distribution px, because the divergence metric has this property that it is always non-negative and is 0 if and only if the constituent distributions match. Okay. If that happens, then if you sample a data point from a normal distribution and pass it through this network, the trained network d theta star, then the samples that we will be getting at the output of this neural network would be samples from px, because now p theta star is close to px by construction. Okay. This is the general principle, and we stopped the previous session by asking the following questions: that how do we compute divergence metrics without knowing neither of p theta and px, right? So now all we have are samples drawn from px. We also know how to get samples from p theta, because obtaining sample from p theta is easy by design, because all you need to do is sample a z, okay, which is from an arbitrary distribution, pass it through the g function, and whatever samples you are getting at the output of this neural network are nothing but the samples from p theta. So we have samples from px, we have samples from p theta. However, we neither know px nor we know p theta. Okay, we don't know what the underlying density functions are, but we have samples from it. And the other question that we ask is, what should be the choice of the divergence metric that we would be using? The third relevant question is how to choose the particular g theta, okay, which says that if you choose a p theta, then you are choosing if you are choosing the function g theta, then in turn you are choosing p theta as well. What choices can one make on g theta? The other relevant question that we asked is, how do we solve the optimization problem of minimizing the divergence metric? Okay. So these are the questions that one should ask if one is interested in constructing a generative model using the push forward method that we just looked at. So now variational divergence minimization, which we will be going to look at now, is no different from the push forward method that we just saw. Okay. So let us continue. Now we will be looking at these class of methods called variational divergence minimization. We will be looking at the method of variational divergence minimization. Now to start with, let us define, the first thing that we should do is define divergence metric between distributions. Recall that one of the key ingredients of building a generative model is to define a distributional divergence metric or divergence metric between distributions. Now let us do that. Let us define a class of distributional divergence metrics called the f-Divergence. f-Divergence. So now given two probability distribution functions, with the corresponding density functions denoted by px and p theta, the f-Divergence between them is denoted as follows. The f-Divergence is defined as follows. It is typically denoted by df, and within the parenthesis we write the density functions corresponding to the distributions which we are measuring the divergences between. So please note that I have assumed that the underlying distribution functions have well defined probability density functions here, and I'm also assuming that the underlying random variables are continuous random variables here. There are equivalent definitions of f-Divergences for the cases where the density functions are not well defined and the random variables are discrete. But since most of the generative models that we will be looking at, the random variables are continuous and density functions are well defined and they exist, I am defining the f-Divergences for this special case where we have the density functions well defined and the underlying random variables are continuous. So the f-Divergence between px and p theta is defined as the integral of p theta valued at x times f of px valued at x over p theta at x dx, and the integral is over the space over which the random variables are defined. Now here f of u is an arbitrary convex function defined from positive real numbers to real numbers. It's a convex left semi-continuous function with the value of the function at 1 being equal to 0. Now, if you look at the definition, and where x is the space on which the distributions px and p theta are supported. Typically, this space happens to be Rd, the d-dimensional real space, because that is where our data is coming from. Now, you please note that f here is any function that is convex and left semi-continuous such that f of 1 equal to 0. So, one can choose an f which has this particular properties, and that particular any particular choice of f is going to give you one divergence metric that has special properties. Now, u here is a dummy variable here. So, f is a function from positive real numbers to real numbers. So, please note that this is a well-defined quantity, because what we are taking here is a ratio of density functions evaluated at the same point. Now, by definition, density functions are non-negative. Therefore, the ratio of two density functions evaluated at the same point is going to be a non-negative quantity, rather a positive quantity. So, now and the range space of density functions are also scalar, right. So, in despite the fact that x here is a d-dimensional random vector, when you evaluate the density function at that particular point, the density function evaluates to a positive real number. Therefore, the ratio of two density functions is going to be another positive real number, and therefore, f of a positive real number is well defined, right. And the f function by definition is a convex function which is left semi-continuous with the value of the function at 1 being equal to 0. Okay. Now, okay, so what are the properties of this f-Divergence? See, the properties that we need are the following. Properties of f-Divergence are as follows. One, f-Divergence for all f, for any f, is non-negative, okay, for any choice of f. So, this is one property that we desire, because we want the divergence metric between two distributions to be always a non-negative quantity, right. So, this is by construction f-Divergence is non-negative for any choice of f. The other important property that is of importance to us is that the f-Divergence between any pair of distributions will be 0 if and only if the two distributions are exactly equal. Okay. So, we will use both of these properties for our case while constructing generative models. Now, recall our goal was to build a generative model such that the distributional divergence between the true distribution and the model distribution is going to be 0. Now, if we take the divergence metric as the f-Divergence, right, then by these two properties, that it is always non-negative and it will go to 0 only when the underlying distributions match, we can use this distributional divergence metric for the case of for the purpose of building the generative model. Okay. Now, let us look at some examples of this f-Divergence. Examples of f-Divergence. Now, if f of u is u log u, okay, then the corresponding f-Divergence will be the famous Kullback-Leibler divergence or Kehl divergence. Okay. It is very easy to see that with this particular choice of f-Divergence, the underlying f function, the underlying f-Divergence becomes the Kehl divergence. Just do the algebra very quickly. So, df between px and p theta for this particular case will be, recall the definition, it will be integral over x. We have p theta of x, f of px by p theta dx. So, this is the definition of the f-Divergence. Now substituting u log u for f function will give us the following. So it will be, so now u will be the ratio of px and p theta. Therefore, this would be u, that is px divided by p theta x times log u. So u is again px divided by p theta x dx. Now this p theta cancels away, so which would make px log px over p theta, px over p theta, which is the definition of the famous Kerr divergence, right? So now Kerr divergence is a special case of f-Divergence, which this particular choice of the f function. Okay, so now as you can see, this f-Divergence will give you access to a large family of divergence metrics, okay, that can be used for different purposes. Now if for those of you who know, Kerr divergence is not known to be symmetric. What do you mean by that? If you consider the Kerr divergence between distributions px and p theta, okay, this is not the same as the Kerr divergence between the distribution p theta and px. Okay, now there are consequences of Kerr divergence not being symmetric. Okay, so now if one does not want to use Kerr divergence for, by the way, this is called the forward Kerr divergence, and this is referred to as the reverse Kerr divergence in the literature. Now, for whatever reason, one does not want to use Kerr divergence as the divergence metric while solving or while building the generative model, because of the fact that it is not symmetric. One can use a different divergence metric, and which would come with the property of its own while building the generative models. So now this motivates us to, this justifies why one needs to look at a large family of divergence metrics, okay, because different choices for this f function is going to give us different divergence metrics that would possess different properties. Okay, so this was one example of the f-Divergence. The other example could be where f function is given by half u log u minus u plus 1 log u plus 1 over 2. Okay. So if you choose this f to be this way, then the corresponding f-Divergence is called the Jensen-Shannon divergence or JS divergence. A version of this is what is used in the famous generative adversarial network. We will see that as we move on. So this is the definition of the Jensen-Shannon divergence. The other famous choice of f function is half times the modulus of u minus 1, and this particular corresponding f-Divergence is called the total variation distance or TV distance. Okay, so now the summary is that by the way, all the functions that we looked at, the f function, obey these properties, that it is from r plus to r, they are convex, and they are left semi-continuous with f of 1 equal to 0. One can easily verify that. Now the summary is that by choosing a particular f-Divergence, one gets a particular f function, one gets access to an f-Divergence with certain properties. Okay. Now, different choices for the f function will lead to different divergence metric, and therefore different properties in the way the generative model is going to be built. Now, the next thing that we should do is that given a particular f-Divergence, I will describe a generic algorithm that is used to construct a generative model using the push forward method that we saw by minimizing any f-Divergence. Okay. So now after that, what we will do is that we will look at a particular example by fixing a particular f-Divergence and see how does that converge into the famous algorithm of generative adversarial networks. Okay. So that is the idea.